Good afternoon from Colombia. My name is Carlos Arteta, and today I will be bringing to you some work we've been doing with my students, José Padilla and Víctor Ceballos, here at Universidad del Norte in Barranquilla. The title of my presentation is Risk-Based Assessment of the Response of ACI 318 Compliant Moment Frames with Intermediate Detailings. We are wondering if the ACI 318 compliant RC intermediate moment frames require a strong column with beam provisions for acceptable performance. As of today, according to ACI 318-19, they are not required, but the question arises, will these frames behave properly under seismic shaking with intermediate intensity, given that the columns might be weaker than the beams? The reinforced concrete intermediate moment frames are allowed to be used in seismic design category C without any high limit. On the left-hand side, we have some plausible sites within the United States of America, and we selected a site in Montana for further study. According to ASCE 716, the seismic design coefficients are R equal to 5, CD equal to 4.5, and omega 0 equal to 3. For the risk-based analysis, we decided to use the conditional scenario spectral as a hazard-consistent ground motion selection technique. With the CSS, we assign rate of occurrences to the ground motions based on their intensity and spectral shape. With this information, we can simulate the hazard at a site with our ground motion set. Here I'm showing you the hazard curves from a PSHA at the site of interest for different periods, 1 second all the way to 3.5 seconds. And in dashed lines, I'm showing you the recover hazard with our ground motion set. So we can say that our ground motion set represents the hazard at a site from 50 to 10,000 years of return period. To select these ground motions, we need to discretize the hazard into different return periods. Here we have UHS for various return periods, including the demand at the MCE and the DBE level. The ground motion selection from one of these levels or hazard levels look like this. We have to estimate a CMS, the variability around it, which we call the CS, and do the ground motions to follow the distribution of the accelerations within this range. Given that we had to run many archetypes for the study to be valid, we developed RC-FIAP, which is the Reinforced Concrete Frame Inelastic Analysis Platform, which is an open platform developed by Víctor Ceballos, one of my students in OpenSysPy. The platform lets the user introduce material parameters, geometric parameters of beam and columns, a vector of height, a vector of spans, some framing loading, some tributary seismic loading, also some design parameters per ASCE 716, and with a simple click, you can design the frames as ordinary, intermediate, or even a special, enforcing or not the column, certain column to beam strength ratio. After the design is performed by the structure, by the platform, the drift revision and design GUI appears, and you can check if the drift limits are compliant with the expectation. Also, within each intersection of beams and columns, you have the calculation of the column to beam strength ratio, and there is a spreadsheet on the right-hand side where the user can change the spacing of the hoops or the amount of transfer and longitudinal reinforcement. With that done, and a single click, an OpenSys model is created. So the whole idea of RC-FIAP is to eliminate the necessity to program complicated models and to focus on the response. So here I'm showing the nonlinear analysis GUI, where you can perform pushover analysis. And in the dynamic analysis tab, you can perform incremental dynamic analysis, or you can perform a conditional scenario spectra type of analysis, which is the type of analysis that we are interested in. These are called risk-based analysis because the ground motions, as I explained before, had some rate of occurrence assigned to them. So when you perform the pushover, this is what we call the plastic hinge projector. We can observe here the display shape of the frame after the analysis is performed, and at the beam and column ends we have the limited state per ASC 41 where the structural elements are at. Also here we have the location of the maximum deformation along the height of the structure for different drift ratios, which allow the user to understand if there is going to be or not localization. On the dynamic analysis portion of the platform, one will obtain a set of pairs of intensity measure, in this case SA at T1, and a structural response. In this case, I'm showing this maximum story drift ratio, and one can construct fragility curves with ease. The variables of interest for this research include frame type, height, and maximum drift ratio allowed. On the left-hand side here, we have what we call the perimeter frames, in which the seismic loading is taken by the frames at the edge, while the gravity loading is taken by the columns in the middle of the structure. Special frames include frames in each of the axes. On the left-hand side, we have a system that is typical of the US, while this one on the right-hand side is more typical of other Latin American countries. We consider 4, 8, 16, and 24 story frames, and the maximum allowable drift was constrained to 1, 1.5, and 2%. The latter one is the maximum allowed drift by ASC 716. According to the proportioning of the frame, we had two types of frames, what we call naturally strong column models, in which we limited the height of the beams to be maximum equal to the height of the columns, and we have also deep beam models to excite some localization problems that may arise. Here we have a plot trend that shows how the first mode period scales with the number of stories. So the typical value of n/10 applies for perimeter frames that are designed for a 1% maximum story drift ratio, but the denominator diminishes all the way to 7 when we allow more flexible frames. We can learn some patterns of behavior from the static response domain, meaning the pushover curves. A typical pushover curve in this study looks like this. We have a distribution of plastic hinging along the height of the structure at the beam and column ends. We have some distribution of drift along the building height, and two values of interest from these pushover curves are the maximum base shear normalized by the seismic weight that the structure can attain, and also the overstrength factor, which is the ratio between this number and the seismic design coefficient. Here we can see a power trend of the maximum base shear in terms of the number of stories. You can see here that the perimeter frames are a little bit weaker with respect to the spatial frames. Also, in terms of the omega sub-zero value, which is set as a constant value equal to 3 per ASC 716, we note that except for the spatial frames whose maximum allowable drift in design was 1%, the value that is given by ASC 7 is a conservative value for almost all the frames and all heights that we consider. Here we started understanding how the drift was distributed along the height. So when we gave the name of the naturally strong column buildings to these frames that I'm showing on the top left-hand side of the slide, it is coming from this type of analysis. We saw a nice distribution of demand at the beam ends, which we call a beam mechanism. There's almost no localization. On the other side, when we add the deep beam buildings, in which we force the beams to be stronger than the columns, we can see that there is some localizations in the demand at the plastic hinge level, and also in the drift level, either in the first floor, upper stories, or some few story mechanisms. So after we did the analysis in this static space, we selected some models that are worthy of further analysis in the dynamic domain. Basically, we focus on the perimeter frames. We kept the strong columns, or the naturally strong columns, and the deep beam models to compare them. We focus on the two limit design drift, 1% and 2%, and we limit the frame height in the study all from 4 to 16 stories. So here on the pushover curves, you can see that the dashed lines are the deep beam models, and you can it is easy to notice that those with 2% drift ratio are weaker than the others, and there is a limited ductility capacity for those with deep beams. The dynamic response of the frames is assessed through the CSS runs, which allow us to estimate engineering demand parameter exceedance curves. The variables of interest comprise the story drift ratio, or the maximum story drift ratio, the maximum column end rotations. Here I'm contrasting the distribution of column end rotations to the limit stays of intermediate occupancy, life safety, and collapse prevention per ASC 41. And also we are interested in the relationship between the capacity and demand at for shear of the columns. The fragility curves for the maximum story drift ratio of the first story frames look like this. Each of the figures shows the probability of exceeding different levels of story drift ratio. So the green curve is for 1%, the yellow curve for 2%, and the red curves for 4%. Highlighted in each of these figures are, let's say, the weaker buildings, which are those designed for a 2% story drift ratio and deep beams. If we compare the demand at the MCE level with the probability of exceeding the 4% story drift ratio, which is close to collapse, we notice a low probability, which indicates that these buildings might not be in danger if the MCE level demand is sought by the building. Similar conclusions can be gathered for the plastic hinge rotations. Here, green indicates immediate occupancy, yellow indicates life safety, and the red ones indicate collapse prevention. Again, when we compare the probability of exceeding the collapse prevention limit, we can see that at the MCE level, the probability is low. The type of analysis shown before with EDP exceedance curves is in line with FIMA P695 type of methodologies, but we can answer more interesting questions if we include the rate of occurrence of the ground motions into the equation. For example, we can calculate the annual frequency of exceedance, or the inverse of the return period of certain EDPs. In this figure, I am showing the risk curve of the maximum story drift ratio of the 4-story frame. We have here 4 curves, one for each of the buildings studied, but we are highlighting the deep beam building with a 2% story drift ratio limit during the design, which is the one with the higher risk. With these curves highlighted in horizontal lines are the different return periods, for example, 500 or 2500 years return period. Now we can ask and enter the figure from the x-axis and ask the question, what is the return period for a maximum story drift ratio of 1%, 2%, or 4% close to collapse? For this particular example, we see that the building with the higher risk is that of the deep beam building with a 2% drift ratio limit, and the return period of the drift ratio that is close to that of collapse is about 4,000 years. Similar trend can be can be seen for the 8 and 16-story buildings. So here we can say, hey, you know what? The drift demand that is riskier to the structure is rare. Why rare? Because we define 4,000 years as rare, but this will depend on the type of structure that we are studying. For example, if we go to a nuclear plant, the answer will be different. The same type of conclusion occurs for the rotation of the beam ends. We can see that the 4-story building is demanded beyond the 4,000 years for the collapse prevention limit. And we can see that the immediate occupancy is close to the 1,000-year return period. So we can say that the building will behave adequately under this intermediate seismic hazard. Again, for the structure, for the demand in terms of shear, on the x-axis here we have the maximum shear demand on the column divided by its nominal capacity. The limit is 1, and we can see here also that it is not plausible that the shear capacity is exceeded by the intermediate seismic hazard on the buildings, even the weaker buildings. So the conclusions: this work evaluated the seismic response of a set of ACI 318-19 compliant intermediate moment frames from a deterministic and risk-based point of view. The variables of interest included the type of framing, the building height, design drift, and beam versus column proportioning. The global level of response of interest included the maximum story drift ratio demand, and the column local level of response of interest included the rotation and the shear demand. The results suggest that the response of the frame was satisfactory for demand levels with a return period up to 4,000 years. So, for the type of frames evaluated and the limit of this study, we can say that the strong column weak beam provision might not be required by the intermediate moment frames under intermediate seismic hazard. With that, I want to thank you and say goodbye.